hope you are able to see the screen. Is my screen visible? I need an acknowledgement from your
Yes.
end. Okay. So you're able to see the questionnaires, what questions I have given to you or as an assignment. So you hear most of the thing because we have very less number of classes. We could able to cover one module only. But since we are also associated with uh, the 1 minute, just 1 second. Yeah, lab. Some of the lab experiments also related to your power electronics circuits, power electronics and instrumentation, where you can also concentrate on those images what I have shown shared with you. I have shared two images to you. That is SCR characteristics and rectifiers and all. Even concentrated on them also, so that you can easily write your assignment. Moving ahead, I think people are joining. Let them join. See, with first question, what it is? With neat diagram, explain the working principles of a power electronic systems. Illustrate the functionalities of the power modulator with suitable example. See, clearly you should read the questions carefully. Don't simply read off of the question and write your answers. You will be losing the marks. So my suggestion here is read till the end of the question. The first question, whether it is there. With suitable examples we are given. So suitable example you can write on your own. I have given many examples when I'm explaining that one. You can write the examples on your own itself. Fine. Let me go ahead for the first question. The first question looks like this. For electronic systems, though it is given in only one slide, but you need to explain this one. Elaborate each block of this particular block diagram. What do you mean by power source? From where exactly you are going to get the power source? Generally, it is a 230 volts power source. We are going to get that one. So we need to go for 230 volts power source and we need to modulate that. Power modulator, major functionalities of the power modulator is converts the electrical energy as per our requirement. So I have given you the example of a laptop or a mobile. Laptop, it needs a power supply, a 230 volts power supply. But 230 volts power supply need to be converted as per the laptop power requirement itself. It may be 15 volts, it may be 12 volts, like that. It need to be converted. So that is the major functionalities of power modulator. The power modulator takes the actual 230 volts from the power source, AC source, then it's going to modulate that. Once it is modulated, then it will be applied to the motor, a motor which is using that power. Maybe in your laptop there may be a motor or may not be a motor. Okay, so motor is to drive the device over there, and to that motor we may be connected some load. I have given the example of your elevator. Elevator need to move up or move to down. So the elevator is connected with a motor. Motor has to be rotated. For that one required power, we should get it. So from the power source, a required power in the required format will be modulated and it will be given to motor. Motor will take that power and it will rotate. And once the motor is rotated, the load, whatever the load which is connected to that motor, will be getting the power and it's going to move or it's going to operate that one. There may be some requirement, some sensing devices where they sense, based on the sensing, there is a control unit will be there. A beautiful example of your this particular power electronic system is your elevator itself. You can go for it. There are so many sensing units which are available. From the outside, some people will push the button like they need to move up or they need to move down. Or inside the elevator only, people will be keep on pressing the various buttons like they may switch on the fan, they may switch off the fan, and there may be a alarm will be there. All those things are sensing devices. They're going to give the inputs over there. Based on the input, a control unit once again will send the signal to the power modulator what exactly it has to do, what exactly a power modulator has to do that one. Our power modulators keep changing the power and it's going to give that one to the motor. Motor will accordingly it's going to operate that one. So you supposed to write the block diagram neatly. Once it has been written, then you should explain each block of that one. What do you mean by power source? What do you mean by power modulator? What is a motor? What exactly a motor is going to do? What is the type of the load you are going to have? And what are the different types of sensing devices which are connected to that one? Once it is sensed, it will be sent to a control unit, and control unit will take care of sending the information to power modulator. So one statement is not sufficient. You need to explain them in detail, depending on the marks. If it is 4 marks, it's okay. If it is 3 marks, it's okay. If it is 10 marks, you have to elaborately have to explain that much. So here we need to concentrate more on the question says that one illustrate the functionalities of the power modulator with suitable example. Here is the illustrate the functionalities of the power modulator with suitable example. This is what we have to do. Here it has been given only 3-4 statements, but you should explain them little bit detail. Power modulator performs the following operation, that is converts electrical energy of the source as per requirement of the load. Is there? You have to elaborate this answer. One statement is not sufficient. Similarly, selects the mode of the operation. It's going to select the mode, what type of which mode it has to work. There are various modes are there. You're supposed to mention that one. Those modes you have to mention. Modulates the flow of the power. Okay, and even I told you about there is only one direction of power will be transmitted. There is no reverse uh, transmission of the power to the source. It should not happen. The power modulator has to take care of that. Power modulator has to control the flow of the power and flow of the current also. There is no reverse flow of the current. That is very, very important. That statement is very, very important. If you don't give that statement, you may lose the marks because that is the actual functionalities of the power modulator. Hope what I'm giving, what I'm explaining, you're able to get those information. Any issues? So that if there is no issues, I can continue over there. Shall I continue?
Yes, sir.
I want, yeah. So good number of attendance is there. Very good. And finally, during the transient operation, start, brake, and speed reversal. That is what speed reversal, starting and brake, putting a brake off the front. See, take an example of your elevator. It need to start and it should put a brake. It should stop, then reverse. It should reverse that because speed reversal. Elevator has to reverse, the motor has to rotate in reverse direction. All those things has to be taken care by the power modulator itself. Initially, it will be rotating clockwise and it will keep moving up. The elevator is moving up till the last floor, the final floor. And once it is reached, if there is any inputs come from the outside or inside of the elevator saying that it needs to move down, then it should go in the reverse direction. The motor has to rotate reverse direction. How it will rotate? The modulator will take care of that. So all these with a suitable example, you should explain them. If you explain it, you are going to get good marks. If you give the good examples, you can give the example of a laptop, you can give the example of the mobile, you can give the example of an elevator, anything which you feel that it is suitable for your power electronic system, then you can explain. You can give that example and explain that. That is the first question. Next question. With neat circuit diagram, explain the operations of the phase control rectifier. What are the applications of it? See here, I am stressing once again. Read the question fully. I need to explain the phase control rectifier. What do you mean by phase control rectifier? That is AC to DC. How exactly AC to DC is going to be converted? That is what required. So we'll move on. Phase control rectifier, that is AC to DC. And here also it's given in only one slide. You should explain them in detail. What I mean by phase control rectifier, how exactly phase will be controlled, everything in detail you should explain with a suitable diagram. If you ask like phase control rectifier, so you need to draw the circuit diagram for that one, either half wave rectifier or full wave rectifier, and you should explain the what is the current flow, how exactly AC will be converted to DC, what is the input waveform, what is the output waveform you are going to get, what is the ripple, everything you're supposed to explain that. So phase control rectifier, these controllers convert fixed AC voltage to variable DC output. We have already seen this one in our lab. How exactly fixed AC voltage will be converted into variable DC voltage. So I'm having a fixed AC voltage 230 volts that needs to be converted into variable DC voltage like 15 volts, 13 volts, 12 volts, 10 volts, 5 volts like that it should be. But it will be in the form of DC. These converters takes power from one or more AC voltage current sources of a single or multiple phases and delivers to the load, and that will be sent to the load itself. The output variable is a low ripple. See here, output variable is a low ripple DC voltage or a DC current. It will be having a low ripple because we are having a definitely there will be some ripple will be there, some pulsating DC will be there. You should know that one. These control circuits use line voltage for the commutation, so line voltage. Hence, they are called as line commutated or naturally commutated AC to DC converters. This is long back I have explained it. I am just revising it. These circuits include diode rectifiers and single or three phase control circuits. These controls are discussed later. Applications. What are the different applications? Because the question itself is asking what are the different applications of that one. High voltage DC transmission system, DC motor drives, regulated DC power supplies, static variable compensators, wind generator converters, battery charger circuits. These are all some of the examples of the second question. Okay, so moving ahead, we have to go for choppers. What do you mean by chopper? So I'll not go for directly the discussing about the your questions and what do you mean by chopper, where exactly chopper is going to be used, DC to DC conversion. Even I have drawn the circuit diagram on board. I've explained it. How exactly DC to DC conversion is going to be taken care. Okay, those circuit diagram you should know that. If you know the circuit diagram, it will be easy for you. How exactly circuits are going to be converted, DC to DC conversion. Initially, DC input will be there and it will be converted because all these questions they need the circuit diagram. How AC to DC conversion, you have to mention the rectifier. How DC to DC conversion, you should mention that one. DC will be converted to DC. DC input voltage will be there, output voltage will be DC itself. You should draw the circuit diagram and you should explain that. I have drawn this one on board. Those who attended the classes regularly, they can directly come to know that one, how to draw the circuit and how exactly it will be converted. The chopper converts fixed DC voltage input voltage to a variable DC output voltage. The DC output voltage may be different in amplitude than the input source voltage. Definitely. What happens now? Because you are converting, the amplitude may vary. Initially, the DC voltage may be 15 volts, but I am converting that one to 3 volts. Definitely, amplitude changes over here. Choppers are designed using semiconductor devices such as the power transistors, IGBTs, GTOs, power MOSFETs, and thyristors. Using thyristors, we can create the choppers, we can design the choppers. Using MOSFETs, we can design the choppers. Output voltage can be varied statelessly by controlling the duty ratio of the device by low power signals from the control unit. Choppers has either a battery, a solar power DC voltage source, or a line frequency. It may be having a chopper, it may be having DC voltage, it may be having solar power DC voltage, it may be having a battery, or it may be having a line frequency derived DC voltage also. Either it may be 50 hertz or 60 hertz, may be there. With that one, we are going to have a DC. So, what are the applications? The basic applications of choppers are DC drives, subway cars, battery-driven vehicles, electric tractions, switch mode power supply, that is SMPS, we'll call that one. All these things are the applications of your DC to DC converters or choppers. So you should neatly, elaborately, you should explain that one with the circuit diagram. If you don't have the circuit diagram, you will not get the marks. Next. Inverters. DC to AC converters. How DC will be converted into AC. Whenever we have used transistors, all transistors have been used to convert this, where during the first half cycle, two transistor opposite transistors are going to work. During the next half cycle, other two transistors, that is B1, B2 will be in forward bias, and B3, B4 will be in reverse bias. Similarly here, in the second half cycle, B3, B4 will be in forward bias, B1, B2 will be in reverse bias. So an inverter converts a fixed DC voltage to an AC voltage of variable frequency and of fixed or variable magnitude. Magnitude also, either it may be fixed or it may be variable, depends. Depending on our requirement, the magnitude also changes, amplitude also changes. So the practical inverter has either a battery, a solar power DC voltage source, or a line frequency derived DC voltage source. Obviously, DC means it may be battery that will be converted into your AC, or it may be solar power DC that will be converted to AC, or it may be a frequency, that is what we can frequency derived DC voltage will be there, that can also be converted into AC. Inverters are widely used from very low power portable electronic systems such as a flashlight discharge system in a photographic camera to a very high power industry systems. Everywhere, industries without power they cannot work. So we need to convert. If there is no power, DC to AC converter should be there. So your home lighting system, if there is no regular power to your home lighting system, we can have a battery which can be converted into AC signal. DC to AC conversion, that will be done by your inverters. So just recall the diagram what I have written over there. We are having a DC power supply. We have connected 4 transistors. In between there is a load will be there. Transistor 1 and transistor 2 will be working and you're going to get the AC. Similarly, transistor 3 and transistor 4 will be working and you're going to get the AC. Positive, negative, positive, negative, positive, negative, you're going to get. So induction heating supplies, everything will be using your power electronics, that is DC to AC converters. Next, AC to AC converters. Obviously, there are some requirement will be there. AC input will be there and it should be converted to AC. Cycloconverters, we call them as cycloconverters. These circuits converts input power at one frequency to output power at a different frequencies through one stage conversion. It's going to convert them. So applications are AC drives like rotary kilns, multi-microwave AC motors. They are going to be used for your AC to AC conversion. Similarly, AC to AC voltage controllers or AC regulators, the regulators, general regulators, where you need to give a constant power supply. There's no fluctuation. At that time, we are going to use AC regulators, that is AC voltage converters. Lighting control, speed control of a large fans and pumps, electronic tap chargers. Say I'm having a fan, so I need to control the speed of a fan. So I'm going to use a regulator. That is AC regulators. These regulators will control the flow of the current and it will ensure that when the fan will rotate at a constant speed when you give the regulator. Otherwise, if there is a fluctuation, you will not get a proper rotation of the fan, the motor, and fan will not run accordingly. So any lighting system, because lighting also they need a constant power supply, they also use the regulators. Fans, they will be using the regulator. Electronic tap changes. So electronic tap changes, they want to change the taps, they're going to use this particular AC to the AC regulators. So these are the 5 different types of electronic converters. The question is like this: what are the various power converters? Different. Briefly explain the various power converters with suitable circuit diagrams for each. Suitable circuit diagram for each. I have already given this in your class. I have given the circuit diagrams also. You need to note them, work out them, and you should write them in the IA. Otherwise, it's not possible to explain them. What are the applications of power electronics in real time? Briefly explain them. So applications of power electronics in real time, there are so many applications are there. See here. This is the next question. Commercial applications, domestic applications, industrial application, aerospace application, telecommunication application. So these 5 need to be explained. Different types of applications, commercial applications. Any commercial applications which is having the need the power supplies. Okay. like heating system, ventilation, air conditioner, central refrigerators, lighting, computers and office equipment, uninterrupted power supply, elevators and emergency alarm. So all these things you can easily on your own you can write it over there. First of all, you should mention what are the different areas your power electronic systems are going to be. In each area where the utilities you're going to use them. So these five you need to explain that. Transportation, utility system, everything. Next is very important. How exactly a thyristor? What do you mean by thyristor? How exactly a thyristor is going to work? What are the characteristics of the thyristor? With your VI characteristics, you're supposed to explain that. So a thyristor is a four-layer semiconductor device of PNPN structure with three PN junction. It has three terminal, anode, cathode, and gate. Thyristors are manufactured by diffusion. They're going to diffuse and they're going to manufacture. Three terminals are there. Diodes will be having only two terminals, but thyristors will be having three terminals. So all these three terminals is supposed to check it out. What do you mean by anode? What do you mean by cathode? What do you mean by gate? What is the purpose of the gate? How exactly gate is going to trigger your circuit? That is firing angle. We will be knowing triggering angle, firing angle. We should know what do you mean by firing angle, what do you mean by triggering angle. So you should ensure that one during the forward bias, how it's going to work, during the reverse bias, what's going to happen, forward breakdown voltage, avalanche breakdown, we'll call that one. So these things you should know with a timing diagram. See here, with the timing diagram, they have given, okay, yeah, not timing diagram, VI characteristics. With the VA characteristics, you're supposed to explain that one. Anode cathode characteristics of the CR. CR means thyristor. So everything, each point you need to explain it. You should explain the what is forward condition region, what do you mean by forward leakage current, what do you mean by forward blocking region. Then finally, when IG increases, what's going to happen? That is gate current increases. Initially, gate current is zero. As you apply the gate current, your triggering changes. That is your firing angle. A firing angle comes into picture, it's going to trigger, and finally you're going to get the shoot in the current. Shoot in the current. Similarly, when you go for the reverse bias, you'll be in a reverse blocking region and reverse avalanche region. Very, very important reverse avalanche region, you have to explain that. All these entire VI characteristics with your PN junction, that is PN junction, if you explain, it's good. So everything has been explained here. What do you mean by reverse blocking region? What do you mean by forward blocking region? What do you mean forward condition region? Everything you should explain that. Next question, gate characteristics. I have told you there are two regions. One is very low and very high voltage and current will be there. So we should have V minimum, VG minimum, IG minimum, VG maximum, IG maximum. There is gate current and gate voltage. Gate current and gate voltage, we should know that one. So once you know that, it will be easy for you. Okay. So you should know what are the three different diodes we are going to work. A circuit diagram will be there. That circuit gate characteristic circuit diagram. Here is the gate characteristic circuit diagram. You should explain this circuit diagram. What is D1, D2, D3? What is the purpose of D1, D2, D3? If D1, what it will take care, D2, what it will take care, D3, what it will take care, everything you should explain that one. I've already explained this. So D1 serves to limit reverse voltage applied to between anode and gate. So reverse voltage applied between anode and gate, that is D1. You should know that. Similarly, D2 prevents the negative source current. D2 prevents the negative source current. See here, this is D2. A negative source current will be prevented. D1 is between these, okay? D1 is between anode and gate. There is the anode, there is the anode, this is the anode, and this is the gate. So it prevents, limits the reverse voltage, and D2 prevents the negative source, and D3 blocks the positive gate current. coming from the supply. So you have to explain these three lines should be there in your answer, then only it will be. And the diagram, that is VI characteristics. You should know gate source voltage, your current, what is the V, what is I, what is I minimum, what is I maximum, what is the region in between this region only. See here, the region is in between here. In this region only, it's going to work. This is the region where you are going to get calculated the values in this region only. I minimum is this one, I maximum, sorry, I maximum is here. Similarly, V minimum is here, V maximum is here. Between this region, you're going to get the your gate characteristics. You should know that one. S1, S, S2. S1, S, S2. Between this region only, the characteristics can be calculated over there. So this is gate characteristics of SCR. These are the equations. What is PG maximum? You're supposed to calculate VG into IG. We'll be knowing because in between region, the threshold region, in that region only we're going to calculate that. With the pulse firing, if the frequency of firing F is known, the peak instantaneous gate power dissipation P maximum can be calculated with VG into IG, where VG into IG is equal to PG average divided by F into T. Once you know the frequency, you can calculate that. So pulse width should be known. T is the pulse width, F is the frequency. Once you know that one, then you are able to find PG maximum. Okay, the gate power. Okay, gate power maximum we can calculate that. Where F is equal to 1 over T1, you can easily find out. A duty cycle is defined as a ratio of pulse on period to the periodic time of the pulse. So duty cycle also you can calculate delta is equal to T divided by T1. That is the duty cycle. Where 1 over T1 is your F, F into T, you can calculate that. From equation 2.10, you're able to find out PG average is less than the PG maximum. PG average divided by delta is less than the PG maximum. Okay. So this is with respect to gate characteristics. Then what happens if the thyristor is turned on? Okay. When the thyristor is turned on, the thyristor is turned on by increasing the anode current. This can be accomplished in one of the following ways. How exactly we can turn on the thyristor? How exactly we can turn on the thyristor? So first thing is power voltage triggering, thermal or temperature triggering, then radiation triggering, then dV by dt triggering, and gate triggering. These are the 5 different ways of turn on modes, turn on mechanisms. 5 different turn on mechanisms. But under gate triggering, we are going to have the different gate triggering. That is, we are having DC gate triggering, AC gate triggering, and we will be having pulse gate triggering. AC gate triggering, DC gate triggering, pulse gate triggering. So the question directly they have asked in your examination also, what are the different triggering mechanisms? DC, there is gate triggering mechanisms of your thyristor. You should know them and you should explain them. So this is what the questions. Other than that, we'll be having thyristor turn on characteristics, switching characteristics of a thyristor. So this is the diagram, timing diagram, sorry, VI characteristics. You can go for it. What is the thyristor turn on characteristics? Gate current, anode cathode voltage, and power loss. These 4 characteristics you're supposed to write it. Means gate current as increase. Initially it will be 0, then you are going to increase. As the time increases, the gate current is going to be constant. Once it is been done, then your anode current is keep increasing over there. Anode cathode voltage will be decreasing. Then power loss, you're able to identify that. So once you know this, based on this gate current, anode current is increasing, anode cathode voltage is decreasing, and finally we're able to find out the, here you see there, VAK, anode cathode voltage, here we are going to have the IT. So power loss will be VAK into IT. What we are here, it is increasing, here it is decreasing. Okay, up to some level it's going to increase, then you're going to get decreased over that. So once gate current is constant, then only we have to measure that. Once the gate current is constant, then only we start measuring. When only your anode current is increasing, at that time only your anode cathode voltage is decreasing over there up to some. So 0.9 voltage to 0.1 voltage, whatever it is, VA we are having 90% of that point. Okay, totally we are going to get only 80%. 90% to 10% we have to consider. Within that limit only we should calculate that. Always like that only. Sometimes we are going to get 0.2 to 0.8. Here they have taken 0.9 to 0.1. 0.9 voltage to 0.1 voltage, anode cathode voltage. So within this limit, we calculate the anode current, get the anode cathode voltage, multiply them, you're going to get the power loss over there. How exactly power loss comes into picture. So here it is increasing, here it is decreasing, and at one stage it's keep decreasing over. This is the power loss. So depending on your gate current, you're able to identify the anode current, you're able to identify the anode cathode voltage, and you're able to find out the your, that is, power loss. Here it's been explained what do you mean by delay time. This is a time between an instant at which the gate current reaches 90% of its final value and the instance at which the anode current reaches the 10%. Gate current reaches the 90%, anode current reaches the 10%. See the diagram once again. See, gate current reaches the 90%. Okay, from there onwards, anode current reaches the 10%. So between that, you're able to find the what is the voltage. See, 0.1 IT, 0.9 IT. 10% of anode current, 90% of the anode current. 90% of the anode current. From there, your anode current is increasing. But from the 10% of the anode current, you have to start up 90% of the anode current. It's not that from here you have to start. So 10% of the anode current. It may be zero here. It start increasing once your gate current increases to 90%. Your anode current start increasing once your gate current increases 90%. Then once anode current reaches 10%, till 90% you have to consider that. That is what we have considered. 10% of your anode current to 90% of your anode current. There we have calculated your voltage, cathode voltage. In between, you are able to find the loss. Delay time, rise time is the time required for the anode current to rise from 10% on state to 90%. See here, this is the rise time. This is from 10% to 90% is the that is rise time, we'll call it. TR. TR has been considered as a rise time. Okay. TD is a delay time. TR is the rise time. Then spread time, TS. See there, TS is the spread time. It is spreading 90 to 100% whatever is there, that is spread time. Overall, we'll call them as a T on time. Turn on time, T on is the sum of the delay time, rise time, and spread time. The time required for the forward blocking voltage fall from 0.1 to its value in the on stage voltage, 1 to 1.5 voltage, we'll call them. See once again the your diagram from here to here. From here to here, it's going to be considered as a or 0.1. This is TS. Okay. The time required for the forward blocking voltage to fall from 0.1 to its value to the on stage voltage drop. This is what it's going to be. Then turn on time has been explained. Turn on mechanism of the thyristor, which is in the on state. I'll just run through. Now the 5 minutes are there. On state can be turned off by reducing the forward current to a level below the holding current IH. There are various techniques for turning off the various thyristors. In the SCR turn, you read the theory. So this is the turn on mechanism. Okay, it's not required as of now. Not required as of now. I'll just go for one more. See here, you should know that What do you mean by half wave rectifier? What do you mean by full wave rectifier? There is some given control technique, phase angle. Phase angle, I have told you, that is firing angle. How exactly your phase angle is going to convert? Phase angle control, firing angle control. See here, there is a firing angle, 0.7 gate. As the gate increases, this is the pulse, gate pulse. Once the gate pulse is applied, then only your firing angle comes into picture. So there is some voltage which will be cut off. So you're going to get only this much. This has been explained in your theory class long back. So you should know what I mean by firing angle. You should explain that one also. Excitation angle. So firing angle is different. Excitation is an angle different. Excitation angle, current control voltage EC. Once this pulse has been applied, then it's going to stop that one. It's just reverse of your firing angle. Here the pulse is applied, then you are going to start getting. If the pulse is applied, your voltage is getting down. Load voltage is getting down. Is pulse width modulation. You're going to modulate the pulse width. That is turn on and turn off time. Only within that time only you're going to get the voltage. Turn on time, turn off time. Within that time you're going to get the voltage. Even though your pulse is, your signal is like this input signal, but your output will be a pulse comes into picture. So this is half wave rectifier. Lab, you have done that one. You have to explain that. There may be a question on half wave rectifier. There may be a question on full wave rectifier. You have done those in the lab. So kindly read them thoroughly. Half wave rectifier and full wave rectifier. You'll definitely get a question on half wave rectifier and full wave rectifier. Okay, fine. Let me stop it now because 90 members are there. That's good only. Participants. Kindly read those who are eligible because there is some little bit confusions also over there. Whoever is writing the examination, write thoroughly. Today is, what is the date today? 6th. I'm stopping it now. So relax and get ready for your next class itself.